Okay, hi, my name is Michael Fitzgerald, as was just presented, and I'm working at Edith Cowan University. A lot of the stuff I'm talking about I do mainly with Lena Denea at Charles Sturt University and David McKinnon also with me. A lot of my stuff revolves around making high school research in astronomy in the high school happen, and I run this project called Our Solar Siblings, which is an official LCOGT education partner, and it's a style of project that tries to get student research in the high school classroom. I wrote a review a couple of years ago if you want to learn more about these types of projects. But essentially what we try to do is you've got the telescope network, which is a fairly technical facility, and you have a bunch of teachers and students who are generally not technical at all. And we kind of try to bridge the gap between the two things. And essentially, there's a slow delay between the slides. Yes. So here's LCOGT. It's a global telescope network comprised mainly of 1 meter telescopes, of which there's now 16. 6 of the sites have telescopes and 1 is just being commissioned. This is the 1 meter telescope, which is the main workhorse of the network. And here's some images of the domes in South Africa. So students and teachers can obtain images and data from these telescopes. So most of the people in our solar siblings will only kind of get some color images, plan some observations, figure out what kind of objects are in the night sky, and also do a lot of simple photometry to measure a kind of rudimentary Hubble's law, which covers the year 9 and 10 curriculum. Some other students will go further. So in year 11 and 12, or as an independent research project, we have materials where students can go further and do photometry and understand stellar evolution by studying star clusters, and approximately none of them, a very small fraction, actually do want to go on to do actual original research. So I'm just going to run through a few of the students who have gone through already. The earliest pair was Tom and Josh, and there was a globular cluster, NGC 6101, which is incredibly far south, and the last time it had actually been imaged properly was in the 70s on photographic plates, but we knew there was RR Lyrae there. So we spent a lot of time getting observations and eventually ended up writing a paper in PASA where they independently found a distance, reddening, and periods of these RR Lyrae. Lauren, there was a neglected open cluster. We kind of had a look through the catalogue, taught her how to do that. That had been kind of neglected, hadn't really been looked at for a while, and there's much confusion over the estimates of the age, distance, reddening, etc. And so over a period of about a year or two, during her 11 and 12, we kind of went through the data, got a few observation nights, combined it with 2MASS and WISE, and kind of eventually ended up with a paper outlining the results from this cluster. And this will come back later in the piece, but this is an image from the paper where it shows a variety of color magnitude diagrams and a color diagram. There are other students who haven't been published, but there's about 7 girls and a teacher at a Western Sydney high school who are looking at 2 clusters close in the sky, trying to figure out if they have similar enough properties for it to be an open binary cluster. And it looks good, but I want to get some U-band images to check that. We also have a student who is looking at, in class, their class looked at an open cluster, and he got excited because he had a look at the paper and went, oh, there's some variable stars. So his project, self-initiated, was to find and classify all the variable stars in this particular cluster. And he's doing that for a CSIRO Crest Gold Award, which is sort of a program where students can get an award for doing a scientific project of a certain caliber. We also have, in class, we have these people, 5 students at Western Sydney High School who each have an open cluster and are using it for their extended investigation, which is essentially a large essay. And note this thing again, it will turn up. And the last thing, RR Lyrae are fairly simple because they've got very short periods, so they make a very good topic for student research because you can get the data quite quickly. So in the traditional Bessel bands, you can see this is all noisy and yucky. Recently, SDSS bands with a pseudo color and period with this kind of relationship shows very tight fit in the theoretical bands. Of course, it won't look that good in observational, but we're collecting data to test out these new relationships. So that's kind of cute. But there's a difference between what these students need and what scientists need. So the students are very time limited. If you're doing it in the classroom, then you have to have the data back within weeks, a month maximum, and there's only so many hours for teachers to do this sort of stuff. And because students are encountering this for the first time, they really kind of fall off the wagon very quickly if you hit a snag. So you've got to kind of make the process as bulletproof as possible. They also can't use any of the Linux tools or software that actually makes most of our science possible. And the freely available tools in Windows and Mac generally aren't that great. And there's no capacity for them to kind of do image reduction on any grand scale. So most of those tools are in Linux, or you have to pay for amateur kind of level software. From LCOGT, the images come down as rice compressed FZ files, which are easy to unzip in Linux, but impossible to unzip in Windows. And yeah, so there's a lot of stuff that students need on top of what you'd expect to get as a scientist. But most of this prep work is automated by a pipeline I've created. I think the battery's running out in this thing. But basically, I take the LCOGT science kind of output and plug in a pipeline at the end and make kind of educational, user-friendly kind of products. So basically, it'll take any kind of optical, traditional, square image and output photometry, cleaned up images, and other stuff ready to use for the students. It automatically runs at the end of each observatory in the network's nightly observing night after the data's got back to Santa Barbara to their headquarters. So the initial part of the pipeline is that it cleans the image. So cosmic rays and column defects and hot pixels are fairly simple. There's nice Python things that happen. What am I having problems? And if you know a solution to this is satellite trails and blooming. I can't find a good automated way to do this in Linux. If anyone can tell me, that'd be great. So these things I can't do, but they don't tend to be so much of a problem anyway. And then what was a problem a decade ago, putting a world coordinate system on, not so much a problem anymore. That's quite simple. But here's the interesting stuff. So it gets this cleaned up image, and it undertakes a variety of different forms of photometry. So we've got aperture photometry tool, which is in Java, which students can use. That's why it's green. All of the rest of the methods are Linux-based and inaccessible to students. So essentially, these two gold standard stellar photometry methods are undertaken on each of the images. And this is the folder that the teacher gets. Each of the methods has its own folder. Each image has its own file, which has exposure time, date, air mass, lots of useful stuff, MJD. And they're all just comma-separated files, which are RA, DEC, pixel locations, counts, and the estimated error in the counts. So they don't need to use Linux. This has already been done for them. And then, if there's standards inside those sufficient standards over a large enough air mass range, it actually goes and automatically calibrates the images in UBVRI or UGRIS, depending what images come in, and then intercompares between all the methods where source extractor is usually a bit dodgy, but everything else usually agrees pretty well. This outputs a photometric catalog. So it has the positions, and then they're measured UBVRI, 2 mass wise. This is I'll talk about that if you ask, but this is proper motion, how many images were used to get those measurements, and then some cross matches for calibration against APAS and some other things that aren't as interesting. From that catalog, it can be taken into a piece of software called Pisochrome, which essentially displays your observational data as blue dots, and you can actually drive isochrones around on top of the data just using the keyboard. So you can hold down D and it'll decrease or increase the reddening, metallicity, distance, and age, and the students can have a look and explore what happens across various filters and what use these color diagrams are. And this is kind of like the information that's down the bottom. So the project is a continual process of development. As LCOGT is creating that network, there's glitches that come along that have to be solved. And also, I continually bump into problems that I need to solve. So it's a continual process of development, but now it's becoming quite easy for students to undertake research of this caliber in the classroom. So that's my brief overview, but if you know any students who are interested, please send them my way. Also, if you have a crazy idea that you would like to undertake with some optical data, optical telescopes, and you would like it to be tried out with a student, let me know. And if you have an education and public outreach program, I'm quite willing to help you use the telescopes. So the education, official education partner for LCOGT, and they give me X amount of time, and I'm quite happy for any other project to use it as well. So just get in contact if that's the case. And also, not educationally, if you have some optical data that you want to be reduced, I have this kind of blind pipeline that will be possibly helpful for you. So that is me. This is our website. And yeah, if you're interested in any of this, please contact me. Thank you very much.